It is a strange paradox of the modern internet that a massive portion of our cutting-edge web infrastructure still relies on a software project that launched in 1995. This chart shows web server market share across over 1 million top websites from 1995 to 2025. If you track the blue trend line, you can see Apache's footprint, maintaining a staggering grip on the market for 3 decades. Even with intense competition from newer, highly agile platforms like NGINX and Cloudflare, Apache consistently serves as the backbone for millions of live, high-traffic domains. How exactly does 30-year-old code survive the brutal hardware evolution of the web, scaling up to handle the massive concurrency demands of 2025? The answer lies in its core design. Apache's resilience comes from a highly modular architecture that avoids monolithic rigidity, allowing it to adapt dynamically to whatever hardware it runs on. To see how this works, we have to deconstruct Apache's backend. We will start at the metal with hardware concurrency and multiprocessing modules, move into live process state management, and finally map out its strict logical configuration rules. Configuring this stack remains a mandatory capability for any modern Linux system administrator. Understanding Apache forces you to look at server administration as a discipline of deep orchestration, balancing physical hardware constraints with logical security parameters. We begin at the operating system layer, looking at the physical mechanism a server uses to handle thousands of users at the exact same time. Early versions of this software, like Apache 1.3, relied entirely on a process-based model. When the server booted up, a parent node would fork off multiple, completely isolated child processes to handle incoming clients one by one. Because these processes were entirely separated from each other, they could not easily share code or data. Assigning processor time to each isolated box required heavy context switching, making this architecture a massive drain on system memory. Apache 2.0 solved this bottleneck by abstracting the request architecture into multi-processing modules, or MPMs. These modules allow a single expansive process to contain multiple threads, giving the server the ability to compute numerous requests simultaneously within the exact same environment. Threads share memory and data directly. This makes them significantly more lightweight than rigid processes, allowing threaded servers to scale rapidly with high-density traffic. But this efficiency introduces an engineering trade-off. Because that memory is shared, a single misbehaving thread can corrupt the data of all its sibling threads, making the overall system inherently less reliable. To manage this risk, administrators can configure the MPM to act as a purely process-based server for maximum stability, a purely threaded server for sheer volume, or a precise hybrid of both. This entire architecture relies on the Apache Portable Runtime, or APR. It abstracts the network and file access APIs, so these complex threading models run equally well on both Unix and Windows systems. The NPM acts as a crucial abstraction layer, giving administrators the ability to tune their concurrency strategy to the exact physical memory and processor limitations of their specific hardware. Establishing the hardware architecture is only the first step. A system administrator must also exert real-time control over these running processes. A live Apache server operates under a strict user hierarchy. At the top sits a singular, highly privileged parent process, overseeing a pool of lower-privileged child workers. To bind to secure system ports, like port 80, that parent process must be started by the root user. However, as a vital security precaution, the server spawns its actual worker processes under a restricted user and group, typically designated as www data. If an administrator issues a standard hard stop command, the parent receives a termination signal. It immediately kills off all of its children to halt operations. The danger of a hard termination is that any requests currently in progress are instantly destroyed, severing active client connections mid-transfer. To eliminate server downtime during an update, engineers use the graceful restart command. First, the server runs a syntax check on its configuration files. The parent process then advises the existing children to finish their current tasks and exit. As they complete their work, the parent seamlessly replaces them with a new generation of workers that begin serving new traffic immediately. By utilizing operating system-level signal management, administrators actively alter the configuration and behavior of a live web server without dropping a single user connection. With the physical processes running and secured, we now look at the logical rule sets that govern what those workers are actually allowed to serve. Within etc Apache 2, configurations are compartmentalized. A storage directory called Sites Available holds virtual host files, and an active directory called Sites Enabled runs them. Administrators use symbolic links to bridge available files into the enabled directory, toggling sites on and off without deleting underlying configurations. The rules inside these files operate via configuration contexts. Rather than a flat list of commands, Apache enforces a strict nested boundary system. Directives placed in the main configuration file apply globally across the entire server. But by using specific section tags like virtual host, directory, or files, you restrict certain directives to apply only to particular domains, specific folders, or individual documents. The server processes these files line by line, actively enforcing which directives are legally allowed within which specific context. To allow for decentralized control, administrators can enable htaccess files. These local configuration files sit directly inside the web directories, allowing individual web authors to override specific directory behaviors without touching the global server settings. Organizing these nested contexts ensures sysadmins maintain granular security boundaries across thousands of different web assets sharing the exact same machine. To see how these components interact in the real world, we track a single client request as it hits the live server architecture. When the incoming request strikes the server, it instantly navigates through a sequence of hardware and logical checkpoints. The Apache Portable Runtime intercepts the connection, standardizing the network access APIs so the data is processed smoothly, regardless of the host operating system. Next, the active multiprocessing module evaluates system load and assigns the request to an available, lightweight thread spinning securely inside a restricted www data worker process. Finally, that individual thread cross-references the request against the configuration hierarchy, filtering from global server limits all the way down through any local htaccess overrides before delivering the requested file. A functioning web server operates at the precise intersection of physical resource management and rigorous logical rule evaluation. Mastering this architecture, controlling threads, managing process states, and structuring strict configuration contexts separates a basic software user from an architect of high concurrency web infrastructure.